This is a brief screencast. I want to explain insertion sort just to give you some idea of how you count instructions and can sort of see for a particular algorithm the difference between the best case and the worst case. So what we're going to try to do is sort the items in ascending order. And we're going to assume that we have a list of those items or an array of those items. And if you look at that list and you look at the first item, that item's already sorted just as that particular item. So we're just going to look at sublists. So now let's look at the sublist that's the first two items. So looking at the sublist with the first two items, what we're going to do is we compare the second item to the first, and if it's less than, then we want it to come first in the list. So we exchange them. So now we have the first two items in the list are in sorted order. So now let's insert the third item in its proper location, and this in order to get the first three items in sorted order. So we compare the third item to the second, and if it's smaller, then we also compare it to the first. If it's smaller than that, we put it before the first. But if it's bigger than the first, we already know it's smaller than the second, so we know it should go in the second slot. And so we keep doing that. Now that we've got the first three items sorted, then we add the fourth item and get the first four items sorted. And we just continue to do that in a similar fashion until the entire list is sorted. So here's an example. We have a list of all these items. Okay, we start off, and 54 is already in sorted order. So we're going to start our loop here, and we're going to put the first two items in sorted order. The way we do that is compare 26 to 54, and 26 is smaller, so we slide the 54 over to here and put the 26 in the first spot. Now we have two things in sorted order. We take the third item, we compare the third item to 93 to 54. 93 is bigger than 54, so we leave it, it stays put. So now we have the first three items in sorted order. Then the next item is 17. Now, to save the swaps, what we're going to do is we take 17 and we store it away somewhere, and we compare it to 93. And 17 is less than 93, so we're going to slide the 93 over. 17 is less than 54, so we're going to slide the 54 over. 17 is less than 26, so we're going to slide the 26 over, and then we're going to put the 17 in the first slot. Okay, the next item is 77. Okay, we compare 77 to 93. It's greater than less than 93, so we slide the 93 over. It's greater than 54, so we put the 77 where the 93 was. And we just keep doing that until all the items in the list are in sorted order. So here's the code. We're going to have an outer loop, and the outer loop is going to go basically each time through the outer loop, we're going to put another item in its proper position. So we're going to start this Python code, so this one actually represents the second element in the list, and then we go to the end of the list. So the current value, we're going to take index, so this is the item we're trying to find its proper location, and we're going to store the position of where we started, and you'll see what we're going to do. We're going to use this to store it away, and index to keep track of where the item is ultimately supposed to end up. So as long as the position is greater than 0, we look at the previous item and compare it to current value and see if current value is less than it. If its current value is less than it, then we want to move to the next position. So here's how we move to the next. We slide the item over, the one that's in position -1 into position, so we slide it to the right, and then we decrement position, and then we just do this all again until finally current value either drop off the end or current value is less than what's in the position before it. I'm sorry, I said that backwards. Until current value is greater than what's in the position before it. And so finally, we put current value into A-list position. Now, if you go look on the web, you can find simulations of insertion sort, which will show you how the code, walk through the code and how it affects the movement of the elements in the list. So finally, we get to the key point here that I want to make with this, in that if the list is already inserted, then inserting, as you're in the outer loop, you look to put the kth item in its proper position. Well, it's going to be in its proper position, and you only need to check it against the item that comes before it in the list to see that, because it'll be greater than that item. So seeing that it's bigger than that item that comes just before it, you just leave it there. So you only have to do one comparison for each item in the list, namely compare it to the one before. You find out the one before it is smaller, and so you just leave it there. So that means you're going to need n-1 comparisons to sort n items, and then, so that means in the best case, this is big O of n. The worst case is going to be that if the original list is in reverse sorted order. And I'm not going to prove this, but you can sort of see why, because of what happens. When I go to insert the kth element, right, since the list is in reverse order, it's going to go to the front of the list because it's going to be less than all the items that came before it. So you have to compare it to all the k-1 items that came before it, preceding it in the list. Hence, the algorithm will need to do one comparison for the second item, two comparisons for the third item, etc. So the total number of comparisons is going to look like 1 plus 2 plus 3 up to n-1. And that sums to n-1 times n over 2, and hence is big O of n squared. So that's it. Again, if you're having trouble understanding this, I encourage you to either look at a textbook or look at a simulation online and see how the actual code gets reflected in the movement of the elements in the list.